Hello everyone, we're going to be doing our Chapter 8 review today. So starting with section 8.1, this is the section that has the most definitions, so it's going to be a little more lengthy in our review, and then all of the sections we see after that are going to be a little bit shorter as far as like definitions go. So with section 8.1, we have, if you have 3 pastry choices and 2 beverage choices for breakfast, you will have 3 times 2 equals 6 different ways of having breakfast. So this means that if you have 3 options for pastries, 2 options for beverages, then it's going to be 6 different combinations or 6 different outcomes of ways that you can have breakfast. This is an example of the multiplication principle. So this is our multiplication principle. We want to suppose that n choices must be made with m sub 1 ways to make choice 1, m sub 2 ways to make choice 2, and so on with m sub n ways to make choice n. Then there are m1 times m sub 2 times, then we go all the way to m sub n. And there's that many different ways to make an entire sequence of choices. So we saw in our very short example here, we had 3 choices in our first category and 2 choices in our second category. We only had 2 categories, so we multiplied them together, we just got 6. If you're using the multiplication principle and you get a pattern like n times n minus 1 times n minus 2 and goes on until you reach 1, then this is called n factorial, and it's written as n with an exclamation point. So this would be like we saw in the previous examples. If we had 8 factorial or 8 exclamation point, that would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Then we would just end there. So we have factorial notation here. So for any natural number n factorial, or n exclamation point, is equal to n times n minus 1 times n minus 2 times, and then we go all the way down until we get 3 times 2 times 1. Also by definition, 0 factorial is equal to 1, and also 1 factorial is equal to 1. We can also use this notation to show that n factorial is equal to, somehow that got missed. There we go. N factorial is equal to n times n minus 1 factorial for all natural numbers when n is greater than or equal to 2. So we see if we had 8 factorial, that'd be the same thing as saying 8 times 7 factorial. And this is just when any number greater than or equal to greater than or equal to 2. So you can have 2 times 1 factorial, but you wouldn't really write 1 times 0 factorial. So really anything greater than 2. A permutation of R, where R is greater than or equal to 1 element, so a set of n elements, is any specific ordering or arrangement without repetition of the R number of elements. So this just means that we have our permutations here of P of n comma R, where R is less than or equal to n, is the number of permutations of n elements taken R at a time. Then our permutation of n comma R is equal to n factorial divided by n minus R factorial. So what we see here is a permutation. They care about the order, and so we're taking some number out of another number. So we take 3 out of 5, and all the different outcomes we can get of taking 3 out of 5 when order matters. So a caution here, the letter P here represents permutations and not probability. In probability notation, the quantity in parentheses describes an event. In permutation notation, the quantity in parentheses always comprises of 2 numbers. So if you see symbol for capital P, and then you have one number, comma, another number, that's going to be permutation. If you have P of really anything that's not 2 numbers divided by a comma, is going to be most likely a probability. So then we have our permutation of n and n. The number of permutations of a set with n elements is n factorial. That is, the permutations of n comma n is equal to n factorial. So here's another caution. When calculating the number of permutations, the formula Do not try to cancel unlike factorials. For example, 8 factorial divided by 4 factorial is not equal to 2 factorial, because we know that 2 factorial is just 2 times 1, and that's equal to 2. You have to write them out, because when you write them out, you see that 8 factorial becomes 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and 4 factorial is 4 times 3 times 2 times 1. So you can cancel out the 4 times 3 times 2 times 1s, so you can cancel those from the denominator and the numerator. But what you're left with is 8 times 7 times 6 times 5, which is going to be 1,680, which is very different than the number 2. So when you want to cancel out factorials, this is how you have to do it. You have to write them out. You can't just divide evenly by whatever numbers you see before the factorial sign. So on to our very first example. So we have example 1 here. A jackpot company has 4 designs that can be jackets, not jackpot, I don't know where I got that from. A jacket company has 4 designs that can be made with or without hoods. There are 7 color patterns available. How many different types of jackets are available for this company? Man, I'm messing up my words today. All right. So we see here that we have different categories, and then we have a certain number of options for each category. So if we have different categories and different options for each category, and we just want to know all the different types of jackets that are available, we can just use our multiplication principle. So we can say, zoom in a little bit here, we can use our multiplication principle. In this case. So we see there's 4 options for design. That's what colons here. So 4 options for design. There are 7 options for color and 2 options for style. And style is what we're going to consider with or without hood. All right, so we have all of our different options for our different categories. So then what we can do is that we can take, or we can call this, we can label each one of these with a different variable. So we can say M1 is going to be equal to 4. M2 is going to be equal to 7. And M3 is going to be equal to 2. So then using multiplication principles, we can say using our multiplication principle, we get, and remember this is just M sub 1 times M sub 2 times M sub 3. We only have 3 categories, so we only go to 3. And so we know this is just going to be 4 times 7 times 2. And we see here that when we multiply these values together, we're going to end up getting 56 options. So we have 56 options here. So when our question is asking how many different types of jackets are available from this company, 56 options for jackets. So just a little note here. We see that this is a prime example of using the multiplication principle when applicable instead of another more complicated formula. So you're going to see that in cases where you can just use the multiplication principle instead of using a more complicated formula, then it's always wise to do so. So this is one of these examples here, that there's probably different ways that we can calculate this value, but the multiplication principle is going to be the easiest. All right, example 2. In how many ways can 6 dogs be arranged in order to pet if there are 10 dogs from who to choose? So we see here, we will just want to take 6 dogs out of 10 and arrange them in order, or a certain order of some kind. So since we are taking a portion of the total number of dogs and placing them in an order, we're going to use our permutation formula. We see there that n is going to be equal to 10 and r is going to be equal to 6. Then when we put this together, we're going to get our permutation of 10 comma 6 is equal to 10 factorial divided by 10 minus 6 factorial times 6 factorial, oops, sorry, nope, that's it. Then we have 10 factorial divided by 4 factorial. So you can just use a calculator to calculate this, or we can write it out. So I'll write it out for this purpose. So say 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial, and then we have 4 factorial. So we're going to cancel our factorials, and we end up getting 10 times 9 times 8 times 7 times 6 times 5, which when we multiply these values together is going to give us 151,200 ways that we can rearrange 6 dogs in order out of 10. All right, so now that we've learned, or we've gone over section 8.1, we've gone over multiplication principle and permutations, now we can move on to section 8.2. So a subset of items listed without regard to order is called a combination. This is written as C, or a big C, and then parentheses N comma R. So since they're just subsets, they're not ordered like how permutations are. So when we think about permutations, we care about the order. When we think about combinations, we do not. And this is mostly because when we think about order, we can have the same elements but just reordered, and that would be considered different ways or different options. But with combinations, we don't care about what order they're in. It's just the number or the identifiable elements in whatever you're thinking about. So your combinations don't care about order, but permutations do. So we see here combinations of C, or combination of N comma R, denotes the number of combinations of n elements taken r at a time, where r is less than or equal to n. Then our combination of n and r is equal to n factorial divided by n minus r factorial times r factorial. So a caution, when we're making a first decision and a second decision, we're going to multiply to find the total number of ways. When we are making a decision in which the first choice or the second choice are valid choices, we add to find the total number of ways. So this wording is going to be very important when you get to certain problems, because when you see the word and, that means multiplication. When you see the word or, that means addition. So you can definitely get the wrong answer just by misreading a question. All right, so here's a little side-by-side comparison of permutations and combinations. So with permutations, different orderings or arrangements of R objects are different permutations. So we see our permutation of n comma r is equal to n factorial divided by n minus r factorial. So that's the equation. Clue words are going to be arrangement, schedule, or order. And remember that order matters for permutations. Then for combinations, each choice or subset of R objects gives one combination. Orders within the group of R objects do not matter. Then we have our formula, so the combination of n comma r is equal to n factorial divided by n minus r factorial times r factorial. The clue words in this case are going to be group, committee, set, or sample. And we remember that order does not matter. So if you read a question and whatever clue words they may use, or it just sounds like it really should be in order, you can use permutations. If you really think about it and you think, okay, well, this doesn't really sound like it should be in order, but maybe it doesn't have any clue words, then go with combination. So another word of caution is to be stressed that not all counting problems lend themselves to either permutation or combinations. When a tree diagram or multiplication principle can be used directly, it's often best to use it. And that's what we saw with our very first example. So maybe they're not always going to be able to use permutations or combinations, but if you can use something very simple like a tree diagram or multiplication principle, it's always best to just use that. All right, example 3. So from a group of 11 new students, 6 will be selected and each will be assigned a different advisor. And how many ways can they be selected and assigned? So even though in this question, we don't see there's any clue words, or none in our chart here. We do see the first word being group, and that's in our combination, but our final answer, we're not asking about a group. We're saying how many ways can they be selected and assigned. Well, if you think about it, assigned is kind of another way of saying arranged. So we could say, even though we use the word group in the beginning, when we assign them to advisors, we are essentially arranging them. So, since we're essentially arranging them in this case, also because we see that we're going to have 6 students and they're each going to get a different advisor. So that means there's 6 advisors, 6 students. We're going to see all the different combinations in which we can assign different advisors, but they're each going to just have one. So this is why we say, okay, well, we're going to think that order matters in this case, so let's use permutation. So we can say, let's use our permutation formula. Then we see that n is going to be equal to 11 and r is going to be equal to 6. So we take our permutation of 11 and 6. This is going to be 11 factorial divided by 11 minus 6 factorial. This is going to give us 11 factorial divided by 5 factorial. So like I said before, you can enter this right into a calculator or you can write it out by hand. But either way, you should end up getting 3,326,000. Nope, one extra number there. 332,164 ways. All right. 332,640 ways that we can assign a randomly 6 selected students out of 11 and assign them to different advisors. So, like we said before when we were looking at our clue words, there was one clue word that was in this problem, but our final question, or what we really wanted to find, was not using one of these obvious clue words. It was using a different word. So this is one of those problems where you're going to have to use your intuition in order to figure out what formula that you want to use. All right. Then for example 4, of the 2,598,960 different 5-card hands possible from a deck of 52 playing cards, how many would contain the following cards? 4 black cards and 3 red cards. So, we see here, since we're picking a first outcome and then a second outcome, we will be multiplying these answers together to get the total number of outcomes. So remember earlier when we said that if you want one thing and another, you have to multiply your outcomes together. If you want one or another, that's when you would add them together. So we want 4 black cards and 3 red cards, so we need to multiply the answers together, the answers that we get for each case. So there are 26 cards between within both suits, or 13 cards in each suit. So we see order doesn't matter. So we will use the combination formula. All right, so we use the combination formula. We'll say that n is equal to 13 and r is going to be equal to 4. Then we get our combination of 13 and 4. All right, so I originally ran the wrong value here. So we have 26 cards that is going to be within each color of card. So there's going to be 26 red cards and 26 black cards with 13 cards in each same colored suit. So we see there's 13 cards in each suit. So there's going to be 2 suits of black cards and 2 suits of red cards, so 13 in each. All right, so we write out our combination formula. Our n is going to be 26 because we just need 4 black cards. So when we do pick these, this is also supposed to be a 2. There we go. All right, so then when we pick these, we only want 4 black cards, and it doesn't matter which suit, just has to be black. So we have our combination of 26 and 4. So when we write this out, we see we're going to get 26 factorial in our numerator, then 26 minus 4 factorial times 4 factorial. This is going to end up giving us 26 factorial divided by 22 factorial times 4 factorial. So now you can calculate this value on your own, or we can write it out. So we'd say 26 times 25 times 24 times 23 times 22 factorial. Then we have 22 factorial times 4 factorial. We can cancel our 22 factorials, and we end up with 26 times 25, 24 times 23, divided by 4 times 3 times 2 times 1. Then we see that this value is going to be 14,950. So 14,950 different combinations of picking 4 black cards. Then we want to do the same thing for picking 2 red cards. So the same idea, we have 26 red cards in all. And we're picking 2 red cards, so we'll say 26 factorial divided by 26 minus 2 factorial times 2 factorial. This is going to give us 26 factorial divided by 24 factorial times 2 factorial. Then we get 26 times 25 times 24 factorial times 2 factorial. So we can cancel our 24 factorials, and we end up getting 26 times 25 divided by 2 times 1, and this is going to give us 325. Now to find our total number of ways remember, since we're finding 4 black cards and 2 red cards, we need to multiply the final numbers together. So this is going to be 14,950 times 325, and this is going to give us 4,858,750 different ways that we can choose 4 black cards and 2 red cards. All right. So on to our next section, section 8.3. We see that many probability problems involving dependent events that we solved in chapter 7 could also be solved using permutations or combinations. So a caution here is that the problems in the first 2 sections of this chapter asked how many ways a certain operation can be done. The problems in this section ask what is the probability that a certain event occurs. The solution involves answering the questions about how many ways the event and the operation can be done. So if a problem asks how many ways something can be done, the answer must be a non-negative integer. If the problem asks for a probability, the number must be between 0 and 1. So we're seeing here that if we ask how many ways are there to do something, we want to list, or we just want to find the number of ways that we find something. So this is going to be some very large number, just like we saw in all the other sections. But now in section 8.3, we're asking for a probability. So we're going to find the number of ways that we could do some action, and then we're going to divide by the total number of waves. So that's going to give us a value between 0 and 1. And we're going to be using our probability formula from chapter 7, which was the probability of an event E is equal to the number of elements in event E divided by the total number of elements. All right, so example 5 here. The bag contains 5 orange, 4 grape, and 2 apple-flavored candies. You reach in and take 3 pieces at random. Find the probability of picking 2 orange and 1 grape. Zoom in a little bit here. So we can say, since we're picking at random, and we just need a sample of 2 orange and 1 grape candy. Well, candies, since it's 3. We can say that order doesn't matter, and we can use our combination formula. All right, so we can use our combination formula, but we need to know the total number of candies. So we see total number of candies is going to be equal to 11. So we have our total number of candies. We want to know if we take random samples, what are the odds we're going to get 2 orange and 1 grape. So we're going to be picking out a sample of 3. So our total number of candies is 11. Our sample size is 3. So our total number of outcomes is going to be n equals 11, r is equal to 3. We're going to get the combination of 11 and 3, which you know is 11 factorial divided by 11 minus 3 factorial times 3 factorial, which we end up getting 11 factorial divided by 8 factorial times 3 factorial. And this is going to end up giving us, or we're going to leave it in factorial form, since we're going to end up with a more complicated way of solving this. We're just going to leave each of these in factorial form for now. So we have the total number of outcomes is going to be 11 factorial divided by 8 factorial times 3 factorial. So then we can say that finding the outcomes of picking 2 orange candies is going to be n is equal to 5 because there's 5 total orange candies and we want 2 of them. So this is going to be our combination. 5 comma 2 is equal to 5 factorial divided by 5 minus 2 factorial times 2 factorial is equal to 5 factorial times 3 factorial times 2 factorial. Then we want 1 grape candy, and there is 4 grape candies in total, but we only want 1. So we're going to have a combination of 4 comma 1. It's going to give us 4 factorial divided by 4 minus 1 factorial times, 1 factorial, there we go. So this is going to give us 4 factorial divided by 3 factorial times 1 factorial. All right, so now we have all the values that we need. So we see that we want 2 orange and 1 grape. So we know that the total number of outcomes for picking 2 orange and 1 grape candy, their singular outcomes are going to have to be multiplied together, and those will be our total number of events or elements in our event. So when we multiply, when we say, remember to multiply the number of outcomes for 2 orange candies and 1 grape candy. This is going to give us a probability of picking 2 orange and 1 grape candy. This is going to give us our combination of 5, 2, or we say orange, multiplied by our combination of 4, 1, which is grape. And then we're going to divide by a combination of 11, 3. And remember, this is going to be our total. So when we put these together, this is going to give us 5 factorial divided by 3 factorial times 2 factorial times 4 factorial divided by 3 factorial times 1 factorial divided by 11 factorial divided by 3 factorial, or I think it's 8 first, 8 factorial times 3 factorial. So this is our equation that we're going to get. Now you can use a calculator to calculate these values, or you can find each singular value to make it more simple on yourself. Since we left in our factorial forms, I used an online calculator, but you can feel free to calculate each one of these individually and then kind of put them all together. That would be a little easier. So we see our final answer is going to be 0.2424. So this is our probability of taking or getting 2 orange and 1 grape candies out of a bag containing 11 different flavored candies. So we left it in decimal form, but obviously we know this is going to be equal to 24.24%. So almost a quarter. All right, now with example 6, we get a shipment of 13 refrigerators contain 2 that are defective. Find the probability that the sample size of 2 drawn from the original 13 will not contain a defective refrigerator. So if we want to find a probability that our sample will not contain a defective refrigerator. Honestly, I don't know if that's how you spell refrigerator. We first need to find the total number of ways we can choose 2 out of 13. So this will be just all the different ways that we can just pick a sample of 2 out of 13. So we see order doesn't matter. And so we use our combination formula. Then we see that n is going to be equal to 13, and r is equal to 2. So we find our total, so we say total number of combinations. It's going to be our combination of 13 and 2, which we see is 13 factorial divided by 13 minus 2 factorial times 2 factorial. It's going to be 13 factorial divided by 11 factorial times 2 factorial. So you can put this in your calculator right now, or you can write it out. You see it's going to be 13 times 12 times 11 factorial divided by 11 factorial times 2 factorial. Our 11 factorials cancel, and we get 13 times 12 divided by 2 times 1. This is going to end up giving us 78. So we have 78 total outcomes or combinations of picking 2 out of 13 refrigerators. So we say then we see there's our combination of 2 and 0 ways of picking no defective fridges. Then, where we say, oh, and there's C11, 2 ways to choose the 2 out of 11 working fridges. So we see we picked our formulas for the 2 different ways that we can pick fridges. So we say then we get, so our first one being C of 2, 0, which when we write this, we know this is 2 factorial times 2 minus 2 minus 0 factorial times 0 factorial. It's going to be 2 factorial divided by 2 factorial times 0 factorial. This is just going to give us 1. So there's one way to pick a sample of 2 with 0 defective fridges. Then we take a combination of 11 and 2, so this is going to be the combination of ways that we can take 2 working fridges out of the 11 working fridges. Since we know that there's 2 defective fridges out of 13, that means that there's 11 working fridges, and this means that if we want our sample to have only working fridges, then it needs to be 2 of the 11. So we have 11 factorial divided by 11 minus 2 factorial times 2 factorial. It's going to end up being 11 factorial divided by 9 factorial times 2 factorial. Then when we write this out, we know it's going to be 11 times 10 times 9 factorial. We have 9 factorial times 2 factorial. Then our 9's cancel, or our 9 factorials cancel, and we get 11 times 10 divided by 2 times 1. And this is going to end up giving us 55. So we say to solve, we use our probability formula and get the probability of having 0 defective, I'm just going to write DEF for defective, it's going to be equal to a combination of 2 comma 0 times our combination of 11 comma 2 divided by our combination of 13 comma 2. So this will be our total number of outcomes, or total number of combinations. So we know this is going to end up being 1 times 55 divided by 78, which we know just going to simplify to 55 divided by 78. And it doesn't simplify any further in our fraction form, so we can just leave it as that. If it asks for decimal form, then this is going to be equal to about 0.705 or 70.5%. So in problems like these, it can ask you for fraction or decimal form, so definitely make sure to see what it's asking for, because if it asks for a fraction form, you leave in your fraction. If it asks for decimal, or if it says round to however many decimals, you want to use your decimal form. All right, then our last section here is going to be section 8.5. So the most common way to keep track of the individual outcomes of an experiment is to assign a numerical value to each of the different possible outcomes. For an example, we can call the outcomes x and assign values of 1, 2, or 3. In some sense, the values are going to be random, so x would be considered a random variable. So a random variable is a function that assigns a real number to each outcome of an experiment. So in this sense, we can assign them numbers, so even if it's outcomes that are written in or descriptive, then we can have these numbers that are assigned to each one of them, and so then we can actually calculate the probability. So a table that lists all the possible values of a random value with corresponding probabilities is called a probability distribution. There is just one probability for every value of the random variable. This is a probability distribution, or thus, probability distribution defines a function called a probability distribution function, or just a probability function. The information in a probability distribution is often displayed graphically as a special kind of bar graph called a histogram. So we see here in figures 8 and 9, we have 2 different histograms. We see that their probabilities, well, in this case, their probabilities are all about 0.5 or less, but our probabilities are always going to be between 0 and 1. And then we see our x values are, in this case, 0, 1, 2, and 3. And we see that they all kind of vary in height. Sometimes you can write your value kind of at the top like they did in figure 8, or you can not write it and you can just draw the bar graphs. So in working with probability distributions, it is useful to have a concept of the typical or average value that the random variable takes on. So we can use something called an expected value. So suppose the random variable x can take on the n values, x sub 1, x sub 2, x sub 3, all the way until you get to x sub n. Also, suppose the probabilities that these values occur, respectively, are p sub 1, p sub 2, p sub 3, and all the way to p sub n. Then the expected value of the random variable is going to be e of x, which that's how we usually signify expected value, is equal to x sub 1 times p sub 1. So x sub 1, whatever your random variable is, multiplied by its respective probability, plus x sub 2 times p sub 2, plus x sub 3 times p sub 3. Then you go all the way until you get to x sub n times p sub n. So note, the expected value of a random variable may be a number that can't occur in any one trial of the experiment. So maybe all of your outcomes for your trials are whole numbers, but when you calculate your expected value, you get some sort of decimal. Well, that's okay, because the way that expected value works is that you're doing the same thing multiple times for a long period of time, so you're not always going to get an even number or maybe an even number that you find in your trial. It can end up being a decimal since you've been doing it for so long, but that's okay. Then we have our formula for expected value for binomial probability. For binomial probability, which was actually a section that we didn't go over, but this definition is very important. We see that E of x is equal to n times p. In other words, the expected number of successes is the number of trials times the probability of success at each trial. So this would be if you're given some sort of population, or really any sort of number, and then you're only given the probability of success. Then all you need to do is multiply those values together. All right, example 7. We see one option in a roulette game is to bet $5 on black. There are 18 black compartments, 18 red compartments, and 2 non-red or black compartments. If the ball lands elsewhere, you lose your $5 and win nothing. Skipped a line. If the ball lands on black, you get to keep your $5 and you win an additional $5. If the ball lands elsewhere, you lose your $5 and you win nothing. Find the expected payback for this roulette game if you bet $5 on black. All right. So we see there's a total of 38 compartments. So it's 38 in total. There's 18 black compartments, 18 red compartments, and 2 non-red or black compartments. So you add those all together, you get 38. So we have 38 total compartments with 18 chances to land in a black compartment. So our probability of success is 18 divided by 38. And our probability of failure is 20 divided by 38. So this will be all the compartments that are not black. My cat really wants to be in the video, so I have to move her. All right. So then we end up getting, we have our probability of success and our probability of failure. We can say then we know if we win, we will gain $5. And if we lose, we will lose $5. So let's use our expected value formula. Then we get, and what we have here is our first option. So let's say our first option is going to be winning. So our outcome of winning is going to give us a positive $5, and the probability is 18 divided by 38. Let's write this a little bit bigger. 18 divided by 38 plus, and now we have our option of losing. So we're going to lose $5, so we're going to say negative 5 times that probability, which is going to be 20 divided by 38. This is going to be probability of losing. So all we need to do is multiply these values and add them together to find our expected value. So when we do this, we end up getting 2.368, and we just want to add on that last exponent just to kind of get an idea of where we need to be rounding in the end. Plus, and this is going to be negative 2.632. So then when we add these values together, we're going to get negative 0.264. But since we're talking about money in this case, we need to remember to round and then solve for the value of money. So we say this is about negative, or I guess that's in the wrong spot. It's going to be about negative 26 cents, or your expected value of payback is going to be negative 26 cents. So we say in the long run, you're going to owe 26 cents. All right, now for our final example here, we have an insurance company has written 200 policies for $100,000, 600 policies for $25,000, and 1,200 policies for $5,000 for people aged 25. If experience shows that the probability that a person will die at the age of 25 is 0.03, how much can the company expect to pay out during the year that the policies were written? So if we need to find total payout from the company, we need to find how much they wrote in total for each policy. So we get 200 policies were written for $100,000. So the company wrote out $20 million worth of policies for the first policy. It's the first policy written in our question, so we're just going to call it the first policy. Then 600 policies were written for $25,000. So the company wrote out a total of $15 million worth of policies for the second policy. Finally, we see there were 1,200 policies were written for $5,000. So the company wrote out a total of $6 million worth of policies for the third policy. All right, so what we've done here essentially is we found out the total amount worth of each policy that they wrote out in that year. Because we know that each one of these policies is going to be worth X amount of dollars, and we sold or wrote however many number of those policies. And our final answer here is how much can the company expect to pay out during the year the policies are written. So if we're thinking about payout, we need to think about the amount of money that they wrote out in that year, the total amount of money that they wrote out. So this is why we need to find the total amount of money written out for each policy. So now that we've done this, so now that we found the total amount written for each policy, yes, we can use the formula for expected value to find the total payout. So we get, and remember our probability an individual dies at age 25 is equal to 0.03. And this is the same no matter what policy, because all of these policies are written for people at age 25. So the percentage is going to be the exact same. We just need to find the payout. So for our first policy, we know that we wrote out $20 million, and the probability is 0.03. Then we know for our second policy, we wrote out 15 million, and our probability was 0.03. Then for our third policy, we know we wrote out 6 million with a probability of 0.03. So simplifying each one of these values, we end up getting 600,000 plus 450,000 plus 180,000 is going to be equal to the total payout of $1,230,000. So we know the total payout was $1 million, $1,230,000. So that was the total payout the year that these policies were written. All right, so now we've gone through each one of these sections. Do not forget to take your quiz today as usual. As always, if you have any questions at all or any concerns, feel free to email me, pop into my office hours, or submit an anonymous question to the anonymous question form. All right, I will see you all virtually later.